All right, so here's 3.4 part two. Remember, this was basically the chain rule again, or chain rule with exponential functions. I'll say exponentials and logs, like log functions, for example. So remember, the chain rule is when we have one function trapped inside of another, right? And the chain rule is just a tool to deal with that. Now, with the exponentials, so remember, something like e to the x is an exponential. We have to apply the chain rule. So I'm going to write like a generic form of it. So I'm going to say, okay, d du of e to the u. So this is the same thing as saying, very similar as saying d dx of e to the x, kind of like what I did in the previous sections. It's just that u this time can be anything. It's not just going to be x or 1x or something like that. It could be 5x squared. It does not matter. Now, how do we derive this? It's still the chain rule. I'm going to put this in blue right here. So we have one function trapped inside of another. We have this could be an algebraic component, this blue u. It could be a trig thing. It could be anything, but it's trapped inside of this e component. So what do we need to do? Chain it. We have to chain this out. So how do we do that? Right there. Well, we derive the outside part first. So remember, the derivative of e to the x was still e to the x. In this case, though, it's going to be e to the u power, and then times the derivative of u. So it's going to be du dx. So slight change right here. Change this to d dx right here because we're still deriving with respect to x. Okay. There we go. So e to the u times du dx. How does that work? Let's say we have y equals e to the 7x, for example, right? Or I'll say e to the 7x, like this. So again, two different functions, algebra trapped inside the exponential. If we want y prime, well, if we follow this formula, what does it say? Oh, the derivative of e to the u is e to the u times du dx. All right, so if I copy that, what is e to the u? That's the original problem when we haven't done anything to it. So it's still e to the 7x. And then times the derivative of the blue stuff. What's the derivative of 7x? Just 7, like that. Notice we dropped it down to the base level. So then your derivative is just 7 e to the 7x, just like that. And it doesn't matter how crazy the exponent is, okay? Like if we have y equals e to the, and I'll just say sine of x, for example. It's still the chain rule. Why? Because you have one function trapped inside of the other. You have that sine x trapped inside the e component. Now, what do we do for y prime? Well, follow the formula, right? It says derivative e to the u is e to the u times du dx. Well, e to the u is just e to the sine of x. You basically copy the original problem down times the derivative of the blue stuff. What's the derivative of sine of x? It is positive cosine of x. So that's your derivative right there. You can rewrite it and say y prime equals cosine of x e to the sine x, like that. What about if we had, say, f of x equals e to the, and I'll say x squared minus 10x. Or I'll put this in blue. e to the x squared minus 10x. All right. Same thing. You don't care what this exponential part is. You're still going to apply the chain rule. So the chain rule for exponentials says, oh, the derivative of e to whatever is e to whatever times the derivative of whatever. The whatever part was this x squared minus 10x. So what's the derivative of x squared minus 10x? It's 2x minus 10. So then to finish it off, we'll just put this out in the front. Because normally you put algebraic components first, like this, and then trig and exponential stuff afterwards. Make sure you keep this in parentheses right here. Do not just write this, because then you're implying that it's only negative 10 e to the x squared minus 10x, when in fact everything is getting this e to the x squared minus 10x. When I say everything, I'm also saying the 2x as well. So be very careful. Make sure you keep the parentheses right there. Now, what if we had, say, something like this? Y equals tangent of e to the 5x. And we want to find that first derivative. How are we going to do that? This is still the chain rule right here, except now that we basically have three components. We have this 5x that's trapped inside of the e, and then we also have the e that's trapped inside of the tangent. So we have to do the chain rule 3 times right here. But it doesn't matter how many times you do it. So far, we've only been doing it 2 times. If you had to do it 50 times, it's the same process. How does it work? You start from the outside. You derive the outside. You leave everything else alone. Then you keep working your way in bit by bit by bit, deriving the next inner piece and the next inner piece until you're done with all of them. So let's try that out. So first, we need to take the derivative of tangent. The derivative of tangent is secant squared, right? And everything else is left alone right now. So this is still e to the 5x. Now we need to take the derivative of the e to the 5x component. So remember, you can just block this out. What would the derivative of e to the 5x be? It would just be, remember, the derivative of e to whatever is e to whatever times the derivative of whatever. So whatever in this instance was 5x. What's the derivative of 5x? It's just 5. So you see, what do we do right here? First, we derive the outside piece. You always start from the outside and you derive your way in. So we start with the outside piece. Derivative of tangent is secant squared. We left everything else alone. We just dropped it. Then we derived the next component, the e to the 5x. That was also a chain rule, right? Because again, we have a function trapped inside of another, an algebraic trapped inside of an exponential. So the derivative of e to whatever is e to whatever times, and we apply the chain rule again, times the derivative of whatever. So it was e to the derivative of e to the 5x is e to the 5x times the derivative of 5x, which is 5. And to finish it off, we just throw the constant out in the front, or we can throw these two pieces out in the front. So 5 e to the 5x secant squared of e to the 5x. That would be your answer right there. All right. The next derivative we're going to look at is the derivative of logs. Okay. So remember, like if you have the natural log, right? Like natural log of a, for example, remember natural logs are just logs with a base of e, right? That's an e right here. But you even have a button on your calculator for this, right? Natural log. So again, whenever y'all see natural logs, it's just log with the base e of whatever. Now, for the derivative, how does that work? Oh, wait, this comes at a later section. Sorry. We'll get back to that in a little bit, in a few sections from now. So what we're going to look at now are, what if we had, say, this is still an exponential function, but now instead of having e to the x, we have a to the x, where a is greater than 1, okay, or greater than 0. So it's not just e to the x. It could be 2 to the x, 5 to the x, 3.182159 to the x, for example, like that. How do we evaluate that right there? Well, the derivative of this is, chain rule time, is a to the x times the natural log of a times du dx. So I need to change a couple things, make this a u right here. This is a u, put it in blue. This is u, and this is u right here. So again, it's chaining. So the derivative of a to whatever is a to whatever, natural log of a, that's your constant. This should be 1, sorry, times the derivative of the exponential chunk. So again, it's still the chain rule right there. So how does that work? What does that look like? Let's say we have y equals 3 to the x. And we want y prime. Well, if we follow this formula, your a is 3, your x is u. So let's look at that. Let's follow this. It says, oh, derivative of a to whatever is a to whatever. So we just basically copy the original problem down. A to whatever, natural log of a, so that's going to be times the natural log of 3 times du dx, or the derivative of the exponential part. What's the derivative of x? That's just 1. Again, if we follow the derivative of a to something, or a to whatever, some number to whatever, the derivative of some number to whatever is that number to whatever, a to the u in this case, times the natural log of that number, or the a, times the derivative of the exponential part right here. So again, that's where that 1 comes from, because we have to chain the exponential part, and the derivative of x is 1. And then you can say, yeah, 1 times 3, or you could throw that 1 out in the front, or you don't even have to write it out, but we can move this constant, right? Natural log of 3 is a constant. It is a decimal if you were to type it into your calculator, but do not put a decimal answer, okay? Not on WebAssign, not on the test. We want to leave everything in exact form. So it's just basically 3 to the x natural log of 3. That's your final answer right there. Now, what if we had y equals 2 raised to the, and I'll say 4x to the 9th plus 10x squared. Looks crazy, right? But again, it just follows this formula. You don't care what this exponential part is right here. What does the formula for the derivative of the exponential say? It says a to the u, right? A to the u. The derivative of a to the u is a to the u times ln of a times du dx. Let's do that. So a to the u, right? If we follow this, well, a to the u is the original problem. So 2, and then we still have 4x to the 9th plus 10x squared. What's the next part say? Times natural log of a. In this case, that's natural log of 2. Then we do du dx, or derivative of the exponential part, the blue stuff in this instance. What's the derivative of the blue stuff? That's 36 x to the 8th plus 20 x to the 1st. And that's your derivative. And then, of course, we put the constant and the algebraic stuff first. What is that? That's this stuff right here. That's the constant. That's the algebraic stuff. So it's just natural log of 2, 36 x to the 8th plus 20 x to the 1st, and then 2 raised to the 4x to the 9th plus 10x squared, like that. So you don't care what this looks like, a to whatever. The derivative of a to whatever is a whatever, natural log of a, times the derivative of whatever is. What if we had a trig function, right? Like, oh, y equals 4 to the cosine of x. I'll do that, or I'll put it in blue. All right, let's look at that now. It's still a to whatever, right? A to whatever. Now, if we take the derivative, remember the derivative of a to whatever is a to whatever. So 4 to the cosine of x times ln of a. So we have ln of 4 because that's our a, times the derivative of the blue stuff, right? Du dx. Derivative of the blue stuff, or the derivative of cosine, is negative sine of x. And then let's move the constant stuff out in the front, meaning the negative sign, the ln of 4, we can put all that good stuff there. So we have negative ln of 4, and then sine of x, and then 4 to the cosine of x, just like that. That's your derivative. Now, what if I have y equals, I'll say 5 to the cosine of, well, I won't do cosine. I'll do, tangent. Why not? Tangent of, let's see here, nine x to the 7th plus, I'll say minus 4x. Something weird like that right there. So how are we going to do that, right? If you want, we can use the different colors again. Like we're going to have 5, and then to the tangent of 9x to the 7th minus 4x. So it's kind of like chain rule 3 times, right? We have the exponential part, this trig part, and that inner part right there. Where do you start? On the outside. We need to do incorporate this rule first. So a to whatever. The derivative of a to whatever, let's follow this again. It's just a to whatever. So 5, and then tangent of 9x to the 7th minus 4x. And then times ln of a, right? Or ln of 5 times the derivative of the u, right? The u is all this stuff. So we need to take the derivative of tangent of 9x to the 7th minus 4x. That's the chain rule right there, right? So just looking at this component, what do we need to derive first? the outside tangent. What's the derivative of tangent? That is secant squared. So we still have this 9x to the 7th minus 4x component. And then we need to finish off the chain rule by deriving the inside of the trig function, or the purple stuff. So that becomes 63 x to the 7th, 63 times 63 x to the 6th minus 4. So that's your final answer. So let's go out there and rewrite it or clean it all up. So y prime is equal to, we're going to put all the constant stuff and algebraic stuff first. So we're going to have ln of 5, and then this 63 x to the 6th minus 4, got that piece, and then 5 to the tangent of 9x to the 7th minus 4x, and then times this secant squared of 9x to the 7th minus 4x. So as you can see, what do? We started with, you always start with the outside with the chain rule, okay? So you derive that, you leave everything else alone, and then you keep working your way in until you've derived every single chunk. It's always from the outside to the inside chunks. Now, what if we had, I'll say, y equals sine of the cosine of 3x. Something like that. So we have chain rule 3 times, right? I have 3 different colors right here. We have the 3x, the cosine, the sine. But again, you start from the outside. So outside is the sine x. What's the derivative of sine of x? It's cosine of x, or cosine of whatever. Everything else stays the same, though. This is still cosine, and this is still 3x right here. Remember, this does not mean sine times cosine. We're taking the sine of the cosine of 3x. This is not multiplication right here. This is embedded inside of the sine. So we derived the outside first. Derivative of sine is cosine. Everything else stayed the same. Now we go to the next most inner piece, which is the purple part, which is cosine. What's the derivative of cosine? That is negative sine. Guess what, though? We have to write everything else on the inside with it. So we just bring it along, right? So this is times 3x. So we've derived the purple piece, right? That's this. But we need to continue, right? Chain rule again. We have to derive the blue part now. That's the innermost piece. So the derivative of 3x is 3. So now we have successfully derived all of it. But let's again clean it up, right? So y prime in this case is 3 times the negative. So we could say, oh, that's negative 3. And then sine of 3x. And then the cosine of the cosine of 3x. Again, you cannot say, this is not cosine times cosine, is cosine squared, okay? This is cosine squared. See the difference, right? There's x's right here. This is embedded inside of that right there. These two are completely different. Do not multiply and write this. A lot of people do that. No, this is inside of this. Now, what if we had this, like y equals, I will say sine to the 4th of x to the 4th. I'll say, just change it. I'll say x to the sixth. Now, how do we do this one right here? So we have a sine raised to the power of something. Obviously, we're going to have to chain rule 3 times, right? We have 3 different colors. But what do we chain first? Remember, it's always the outermost part. If you have trig functions raised to some power other than 1, then you have to do that exponent first because that's the outermost part. So we need to derive the purple component first. So y prime is, how do we do that? It's the power rule, right? It's something raised to some power. So what do we need to do? We need to bring the 4 down. The sign, we don't touch it yet because we're still deriving the outside. Remember this, the 4th power is the outside chunk this time. That's what goes first. So we have 4 sine cubed. Y, that's the power rule, right? 4 minus 1 is 3 of x to the 6th. That, remember, nothing else changes, right? When you're chaining, you only derive one little chunk at a time. So we've done the purple part. Now we need to move on to the next most inner part, which is the sine part. What is the derivative of sine? So what's the derivative of sine? It's cosine, right? Cosine of everything else on the inside. We don't derive that yet. So we have this. Notice I didn't put cubed right here or the 4th power or anything like that. No, you're basically covering that up. Like you can pretend this doesn't exist. And now we're just looking at, oh, what's the derivative of sine? It's cosine of x to the 6th. And then we finally get to the next innermost piece, which is x to the 6th. What's the derivative of x to the 6th? 6x to the 5th power. So there is our derivative. So again, the outermost piece was this exponential part. So you derive that first. The derivative of whatever to the 4th, you apply the power rule. So it's 4, and we did not change anything else, right? We kept all this other stuff here, but the power rule says we drop this by a power of 1. And on the inside, again, we did not touch that. We did not derive this piece yet. Why? Because we were still deriving the first chunk, which is that all this raised to the 4th power. Once we were done with the purple, right, what do we move on to? The black markers, right? So we had to derive the sine aspect. Okay, again, I didn't derive sine cubed. No, you just derived the sine. Okay, so the derivative of sine was the cosine of whatever. And then finally we went to the innermost piece, the red piece right here. So the derivative of that was 6x to the 5th. And then to clean it up, well, we could say, oh, 4 times 6x to the 5th. That's 24 x to the 5th sine cubed of x to the 6th, and then cosine of x to the 6th, like that. And there is your answer. What if we had this right here, like y equals e, and then I'm gonna put 2x, and then sine of x, like that. So this is a chain rule and a product rule. It's just now it's embedded, right? The product rule is embedded inside of the exponential function right here. So remember, what's the derivative of e to whatever? If you have d dx of e to the u, remember the derivative of e to whatever is e to whatever times the derivative of whatever. So I'm going to call this, I'm going to put f and g up top right here. Why? Because once we get to this du dx, or we derive this exponential part, we have to do product rule right here, right? Got to do that. So product within chain. So just take your time with it, okay? So y prime. remember the derivative of e to whatever is e to whatever. So e to the 2x sine of x times the derivative of whatever. The whatever piece was this 2x times sine of x. So that requires the product rule right here. Remember the product rule says fg prime, right? This is fg prime plus gf prime right there. So f times g prime, well, f is 2x. What's g prime? What's the derivative of sine of x? That is cosine of x. And then plus, so now we're going to gf prime. G was sine of x. And now we have to do f prime, or the derivative of 2x, which is just 2. So this is your derivative. It's all this stuff right here. And you can leave your answer like this, or if you want, you can say, oh, this is e to the 2x sine of x, and then 2x cosine of x plus 2 sine of x. You can move that 2 out in the front, or you should. So this is your final answer right here. But again, what do we have to do? We had an exponential, and then we had a product rule within that. So you're going to have to pay attention and take note of all that stuff. All right, these problems, the directions will just say, you know, derive, or as you're working them out and you have to take the derivative, you're going to have to know eventually that, oh, I'm going to have to do the product rule as I'm chaining this right here, or the quotient rule or whatever. The directions are going to say, hey, by the way, the chain rule is going to be involved, right? Remember, chain rule comes up when you're multiplying two different functions, right? So that was the indicator for that. What if we had like y equals the square root of secant of 2x, something like that. And we want y prime. Now remember, whenever you have roots, you need to rewrite them, right? Better yet, I'll put cubed root. Why not? Let's do that. Let's do cubed root of secant of 2x. So remember, when you have radicals and you're deriving or taking the antiderivative, you need to rewrite that in exponential form. So this is actually, and I'll do it in different colors, 1/3, right? The cubed root of something is the same thing as saying 1/3. And then we have secant of 2x. So 3 different things, right? Chain rule again, right? Chain rule, 3 different colors. Where do we start? The outside chunk. What's the outside chunk? The 1/3. That involves the power rule. So that's going to be 1/3. And then nothing else changes on the inside, right? It's still secant of 2x. But we still have the power rule on the outside. 1/3 minus 1 is negative 2/3. Now we derive the inside. What's the derivative of secant? Remember, the derivative of secant was secant tangent. But in this case, it's going to be secant of 2x. And then tangent of 2x. So remember, that's just the derivative of secant. Derivative of secant, right? If you forgot, like if I do d du or d dx of secant u, it's just secant u tan u and then du dx, because it's chaining like that. So we're not finished with this, right? Because so far we've taken the derivative of the outside, or the 1/3 component. That was the power rule. Then the purple, because that was the next innermost component. So the derivative of secant of 2x is secant 2x tan 2x. And then finally we have to finish it off by taking the derivative of the blue component. So the derivative of 2x is just 2, like that. This is all connected via multiplication. We can multiply a little thing out, right? If you notice, we have 2 and this 1/3. So 2 times a third is 2/3. And then we have, and it doesn't matter if you put this first or that first, it really doesn't matter. So we have secant of 2x, and this quantity raised to the negative 2/3. And then times this component here, secant of 2x tangent of 2x. All right, we'll try one more. Let's say we have y equals, and I'll say cosine to the 5th of 3x to the 7th minus 1, like that. So chain rule 3 times, right? You have 3 different colors right here. Where do you start with? The cosine, the exponential 5, or this 3x to the 7th minus 1? What's the outermost piece? It's the green. So we need to do that first. So y prime is equal to, if we derive the outside first, which is this, that's the power rule. So it's 5. And this is still cosine right here. But this power rule, right, which we're doing 5 minus 1, this becomes a 4 right here. Everything else is still the same. The cosine's still there. This is still 3x to the 7th minus 1. So we've derived the outermost chunk, which was the 5. Now we need to go to the next chunk, or the next innermost chunk, which is the cosine, correct? So now we derive the cosine. What's the derivative of cosine? So again, we don't keep that 4 with it. You're blocking this out. What's the derivative of cosine? It's negative sine. And we still have everything else on the inside of it. So there's still 3x to the 7th minus 1. And then finally, we get to the red. We can derive the innermost piece, the 3x to the 7th minus 1. What's the derivative of that? It is 21x to the 6th. So again, what do? We had to derive the outermost piece, which was the green component. That was the power rule, right? So you bring the 5 out in the front. 5 minus 1 gets us to this 4. Nothing else changes. Then we move to the next innermost piece, which was the cosine. Don't put that 4 here, or don't put a 5 right here. No, you're done with that. We already dealt with that derivative right there. So now we just derive cosine, which is negative sine. And then everything on the inside still stayed the same. Then we move to the next innermost piece, which was the derivative of this, correct? So that's where we're getting 21x to the 6th. What happened to the derivative of 1? Remember, the derivative of any constant is 0. That's why we don't put that, just nothing. And then to finish it off, we can go, oh yeah, negative 5 times 21, right? That is negative 105 x to the 6th. Come on, marker. X to the 6th cosine to the 4th power of 3x to the 7th minus 1. And then sine of 3x to the 7th minus 1. So again, the negative came from here, right? Negative 5 times 21, or you can say 5 times 21 is 105. We have the negative right here. That's like a negative 1 if you want to treat it like that. Negative 1 times 105 is negative 105. So take your time with these, right? It's just they do eventually get, as you can see, very large. And you always have to take into account, oh, do I need to do the product rule or quotient rule? Or is there something else embedded within this chain rule right here? Okay. So that concludes part 2 of section 3.4.